How are you all doing today?
Doing well.
Any questions about any homework or anything before we jump into the Thevenin and Norton stuff? All right, nobody's saying much anything, so let's go ahead and get at it. So this is our first problem that we're going to work today. So let's see how much you guys paid attention. If I was to try to find the Thevenin voltage, what would I be trying to find in this circuit?
The voltage across the open circuit?
Exactly right. So the Thevenin voltage is always an open circuit voltage. So we're told that we want to find the Thevenin voltage with the positive polarity on top. So that means we are trying to find this voltage, VTH. Does anybody have any suggestions on how we might go about figuring out that voltage? So with a Thevenin or Norton equivalent circuit, we can find the Thevenin voltage using any circuit analysis technique that we want to. So I would argue that since we're trying to find the voltage, we should use nodal analysis. That being said, we could just as easily do mesh analysis and figure it out as well. We'll just have to get a little bit creative at the end, since mesh analysis is going to give us a current and we're looking for a voltage. So using nodal analysis, I'm going to choose my bottom node as my reference. And I can identify a node here. So I'm going to call this node 1. I'm about to call it A, but that would be a bad choice. And this guy V2. If my stupid pen thing will behave itself. There we go. So I could also call this node over here on the right-hand side V3. However, I would argue that V2, the nodal voltage V2 and the nodal voltage V3 are representing the same quantity. Can anybody tell me why?
Well, I mean, because it's going to be going from that V3 to that ground, which is 0. So it's just the same as when you're doing nodal analysis. V3 is equal to V Thevenin.
Right, V3 is definitely equal to V Thevenin. I have no problem with that. I'm saying I believe that V2 is also equal to V3 and therefore V Thevenin. So let me ask you guys a question. How much current will flow through the 160 ohm resistor? Can we figure that out just by looking at the circuit? Trying to think of how to pose this question again. Is the 160 ohm resistor right here part of a closed loop able to carry current?
No.
No, right? It's connected in series to an open circuit. Let's see what somebody said in chat. No, okay. So if the 160 ohm resistor is not part of a closed current carrying loop, how much current flows through it?
None.
None. So if there's no current flowing through the 160 ohm resistor, what's the voltage drop over the 160 ohm resistor?
0.
0. So now, can you see why I am saying that V2 and V3 are representing the same quantity?
Yes, sir.
Yes,
Yeah,
sir.
if there's no voltage drop over the 160 ohm resistor, V2 is equal to V3. And so we know that V2 is then equal to VTH. So I've just eliminated one, so going from a 3 equation, 3 unknown system to a 2 equation, 2 unknown system by looking at the circuit and interpreting what's going on. All right, so let's do KCL at node 1. So who wants to start me off there? KCL at node 1 means we want this current, and this current, and add them together and set it equal to 0. So somebody tell me what to do.
So you do just going from starting on the left hand side, you do 1.2 volts divided by 49 ohms. Wait,
So 1.2 volts divided by 49 ohms would give me the current flowing from left to right through the 49 ohm resistor under the assumption that V1 is our reference, but V1 is not our reference. So if we want the current flowing from right to left, the nodal voltage on the right-hand side of the 49 ohm resistor is V1. The voltage on the left-hand side of the resistor with respect to ground is 1.2 volts. So that's why we have V1 minus 1.2 volts, and we divide it by the resistor value, 49 ohms. Who can tell me what the current going down through the 180 ohm resistor is?
It's going to be V1 divided by 180 ohms.
Yeah. So the voltage on the assumed positive polarity terminal, so where the current's leaving from is V1. The current at the terminal, or excuse me, the voltage at the terminal that the current is flowing to is our reference terminal, 0. So it's V1 minus 0 over 180 ohms. What about the current flowing from left to right through the 96 ohm resistor?
V1 minus V2 over 96.
Alrighty, and set all these guys equal to 0. So that is our KCL at node 1 equation. Now let's look at KCL at node 2. So we're going to have this guy to the left, this guy down. Technically, we should have this guy to the right as well, but we know that's 0, so we're not going to worry about including it.
can you get ready for a tripping?
What is the current directed from right to left through the 96 ohm resistor?
V2 minus V1 over 96.
V2 minus V1 over 96 ohms. Alrighty. And what is the current flowing down through the current source?
Negative 0.2 amps.
Alrighty, so we can solve this system of equations. Which means I need to find my calculator. So we have a 2x2 system. Coefficient for V1 is 1 over 49 plus 1 over 180 plus 1 over 96. The coefficient for V2 is negative 1 over 96. And our constant term, when we move it to the right-hand side, is positive 1.2 volts divided by 49 ohms. All right. In our second equation, our coefficient for V1 is negative 1 over 96. The coefficient for V2 is positive 1 over 96. And our constant term is 0.2. If we solve these guys, we get V1 is equal to 8.6 0.646 volts, and V2 is equal to 27.846 volts. And we've discussed previously that V2 is exactly equal to H. So we got this answer. Everybody okay with what we've done here?
Yes, sir.
Anything that wasn't clear? All right, so next we are going to find the Norton current. So who can tell me what the Norton current is? Like how, what do I have to do to find the Norton current?
Make A and B a short circuit.
That's exactly correct. So we short out terminals A and B, and then we measure the current flowing through that short circuit. And is writing terribly. All right. So let's get rid of all of this because we know that that's correct. So how would you guys suggest I determine what my Norton current is?
Mesh analysis.
Mesh. Seems perfectly reasonable. So I'm going to have mesh current I1, a mesh current I2, and a mesh current I3. So I have a super mesh that I have to pay attention to because there is a current source in the middle of the circuit. So I'm going to first write down my current relationship equation. Can anybody tell me what that should be?
I3 minus I2 equals 2.2 amps.
I3 minus I2 is equal to 0.2 amps. That is absolutely correct. Now let's write our KVL equation at our supernode. Excuse me, super mesh. So starting from this bottom left-hand corner and following the mesh around this loop, what are we going to have?
$180 I2 minus I1 plus 96 I2
All right, great so far.
plus 160 I3 is equal to 0.
Equal to 0, right? All right, that is great. So now we have our mesh 1 to take care of, and we'll have our 3 equations. So who can tell me what's going on in mesh 1? Start from the bottom left-hand corner and work our way around this loop.
Plus 1.2 volts.
So it'll be minus. We see the negative terminal first as we follow the current mesh current I1 around its loop. What's next?
Plus 49 I1.
Alrighty, and what is our last term?
$180 times I1 minus I2.
That is correct. Set this guy equal to 0. And now we can solve these 3 guys. So let's see, I have a 3 by 3 system of equations. So in equation 1, my coefficient for I1 is 0. My coefficient for I2 is -1. My coefficient for I3 is +1. And my constant term is 0.2. In equation 2, I have -180 I1. I have 180 plus 96 plus 160 I3. Oh, excuse me. That's so I made a mistake there. 180 plus 96 for I2. And then for I3, I have 160. It's equal to 0. And let's see, in equation 3, I have 49 plus 180 for my coefficient for I1, negative 180 for my coefficient for I2, 0 is my coefficient for I3, and positive 1.2 volts is my constant value term. So I have to solve this system. I get I1 is negative 77.647 milliamps. I2 is negative 105.45 milliamps. And I3 is 94.550 milliamps. So what is I Norton going to be?
And the I3.
Yeah, exactly equal to I3. So we got this answer. So just to be clear here, the Thevenin voltage is found by determining the open circuit voltage across our set of terminals. And the Norton current is found by finding the short circuit current after we short circuit our set of terminals. So our last step then is to determine our Thevenin resistance. Anybody have any ideas how we might go about doing that?
You can use the equation from your notes. R Thevenin equals V Thevenin over I Norton.
Absolutely, that's a perfect way to do it. So 27.846 divided by 0.09455 is 294.51 and some change ohms. So the suggestion was that, sorry, R Thevenin is equal to V Thevenin divided by I Norton, which is perfectly acceptable. What if we wanted to check our work? So we could determine the Thevenin resistance directly, right? And what I mean by that is we can look at the dead network and then find the equivalent resistance of that dead network. A dead network is one in which all voltage sources, all input sources and current sources are turned off. So who among you remembers how to turn off a voltage source?
You put it as an open circuit.
So to turn off a voltage source, we want to make sure that the voltage is 0. Are we guaranteed that the voltage drop over an open circuit is 0?
No. So
No.
you short it then.
Right. So to turn off a voltage source, you short circuit it because we know that the voltage drop over a short circuit has to be 0. So our voltage source becomes, just a line. Then we have our 49 ohm resistor, our 180 ohm resistor, our 96 ohm resistor. How do we turn off our current source?
An open circuit.
An open circuit, right? Because in an open circuit, no current can flow through. And to turn off a current source, we want it to represent 0 current with any possible amount of voltage. So I'm just going to have effectively an open circuit here. Then I have this 160 ohm resistor. Here is terminal A, and here is terminal B. So hopefully everybody can see that the equivalent resistance seen between terminals A and B is going to be a 160 ohm resistor in series with a 96 ohm resistor, and that is in series with the parallel combination of a 49 ohm resistor and a 180 ohm resistor. Everybody see what I just talked about?
Yes, sir.
So the 160 and the 96 are in series because they share the single point of interconnection. The 49 and the 180 are in parallel because they share this node and this node. And then as we follow everything around, we have 160 plus 96 plus the parallel combination. And so just to check our answers, 160 plus 96 plus 49 times 180 over 49 plus 180 gives me 294.515 ohms. So if our Thevenin resistance matches what we got by dividing V Thevenin by I Norton, then we have not made any mistakes. So that's a Thevenin and the Thevenin and Norton analysis has a built-in way for you to check your answers. So I like it a lot. All right, any questions on this problem that we just solved? All righty, then let's move along to our second problem. So in this one, we don't have an open circuit that we are looking for, the Thevenin voltage across. We're asked instead to find a Thevenin voltage, Norton current, and Thevenin resistance as seen by the 3 ohm resistor. So this is a different analysis process, only slightly, because instead of trying to find it across a set of terminals, we're trying to find it with respect to a particular load resistance. So what that means is that we need to disconnect that resistor and then measure the open circuit voltage where that resistor was. We need to short out that resistor, measure the Norton current through that short circuit, and then for the Thevenin resistance, we open circuit that 3 ohm resistor again and look into the dead network. So for our Thevenin voltage, we are going to be looking at this circuit. And we're told specifically that the positive polarity for the Thevenin voltage is on top. So that means we're solving for this voltage, VTH. So I want to be clear here. Anytime we're trying to find the Thevenin equivalent with respect to a particular component, we need to make sure to take that component out of our circuit to do the analysis. So what do you guys think the most efficient means to determine this Thevenin voltage is?
Could we possibly combine those 2 resistors to the right and then do a source combination to make it a voltage source?
So we can do that. My argument is that necessarily beneficial? So what this person was suggesting, let's see, 5 is that we could make this circuit. So we have our 7 ohm resistor. Let's see, I'm going to put the resistor here. So 5 in parallel with 2 is 5 times 2 over 5 plus 2, so that's 10 over 7 ohms. And then we're going to have minus plus 6.5 times 10 over 7 is 650 over 7 volts. And then here, dang it, is VTH. So let's start with, did I do the source transformation correctly? Anybody?
Yeah, that's right.
All right, anybody have any issue in the order in which I placed my circuit elements or anything like that?
No, sir.
All right, so working under this assumption using our source transformation, what would the next step be in finding our Thevenin voltage?
You could do mesh.
So if we did mesh, there's only one mesh because there's an open circuit in the middle. So really what we would be doing is using Kirchhoff's voltage law to figure out what the current that flows through this single loop circuit is. There's nothing wrong with that whatsoever. It's just, it's not really mesh analysis because we're not setting up a system. So this current, let's call it I, would be negative 18.6 volts plus 7 ohms I plus 10 over 7 ohms I minus 650 over 7 volts is equal to 0. So that means, let's see, 7 plus 10 over 7. So that's 80 over 7. Hold on. No. 7, 49, 59 over 7. 59 over 7 ohms times I is equal to, oh, there's no way in hell I'm going to add 650 over 7 plus 18.6 in my head. That's terrible. Let's see, 650 over 7 plus 18.6, 111.457.
Oh, sir,
Yes.
when you're doing the source transformation, that voltage should be 65 over 7, not 650 over 7.
6.5 times. Yep, you're absolutely right. All right, so 65 over 7 plus 18.6. Come on, work pen thingy. There we go. 27.886 volts. So I is 27.886 divided by 59 over 7. Just to make sure, I'm just going to do 7 plus 10 over 7, in case my mental math was incorrect, as it was with that thing. All right, 3.308 amps. Okay, so now that we know that current, what can we do?
We find out the voltage drop over the resistors.
So how would that be useful? I'm going to take your idea and modify it ever so slightly. I'm going to write a Kirchhoff's voltage law loop around this loop. So I would have negative 18.6 volts plus 7 ohms times our current I, which we know to be 3.308 amps, plus our Thevenin voltage is equal to 0. So that means that VTH is 18.6 volts minus 7 ohms times 3.308 amps. Negative 4.559 volts. So that answer does match what we were supposed to get. So there's nothing remotely wrong with that thought process. However, it is not the most efficient way to solve for the Thevenin voltage. Did anybody have any other suggestions looking back at our original circuit?
The way I solved it was nodal.
Yeah. And it's really not much of nodal technically. It's kind of just doing Kirchhoff's current law at one node. So let me do it this way so it'll go faster. So this node, let's call it VA, is the only unknown. If we choose this to be our reference, we have one unknown voltage. So if we do KVL here, we would have VA minus 7 ohms over 18.6 volts. Oh, excuse me. No, that's so horrifyingly wrong, I'm embarrassed. VA minus 18.6 volts divided by 7 ohms plus 6.5 amps plus VA over 5 plus VA over 2 is equal to 0. One equation, one unknown. We can solve that guy pretty easily. So I have x over 7 plus 6.5 plus x over 5 plus x over 2 is going to be equal to 18.6 over 7. Solve. Peasant calculator is taking its sweet time. VA is equal to negative 4.559 volts. So the exact same result, but we got it in one step instead of 3 or 4. So again, there was nothing remotely wrong with the line of reasoning on the analysis that we did the first time. It's just not the most efficient method. So just wanted to let you guys think about that for a second. All right, Norton Current. What are we going to do to our circuit where the 3 ohm resistor is removed?
You short it out.
Short it out. Okay. So we place the short circuit right here, and we find I Norton. Are there any simplifications that we could make right now? So your likely gut reaction to how to figure out this current would probably be to do mesh analysis. And there's nothing terribly wrong with that. The problem that we would have is that there are 4 meshes, right? So right now, we would have mesh 1, 2, 3, and 4. So based on our circuit as it's drawn with that short circuit over there on the left-hand side, could we determine what the current through, say, the 5 ohm resistor was or the 2 ohm resistor is without actually doing any work?
Wouldn't it be 0?
Exactly, because the 5 ohm resistor and the 2 ohm resistors are shorted out. They are in parallel with the short circuit. So we know that no current is going to flow through this 5 ohm resistor. And no current will flow through this 2 ohm resistor. All the current will flow through the short circuit. So we could just as easily analyze this guy and we would get the correct result. Now, is mesh analysis appropriate here still? Absolutely. But there is a slightly easier way to figure things out as well. Well, I don't know if it's any easier, but I would say it's of equal difficulty. And so what I would suggest here is actually it's effectively superposition. You're going to get the exact same result as mesh. But if we use superposition, when the voltage source is on and the current source is off, I Norton prime would be what? So the voltage source is on and the current source looks like an open circuit. So we
Be
would have,
18.6 over 7.
that's it. When the voltage source is off and the current source is on, what is I Norton double prime?
It was 6.5 times 7.
So let's look at the circuit real quick. So we have a short circuit, a 7 ohm resistor, the short circuit, 6.5 amp source, and we are trying to find this current.
Isn't it just 6.5 or negative 6.5?
Negative 6.5, exactly right. All the current from our current source will flow through the short circuit of our, between our terminals there. So we could have done mesh, set up a system, 2 equations, 2 unknowns, or we can do it this way and we're going to get the exact same result. And we're pretty much going to wind up with the exact same equations, actually. So let us see then. All right, so 18.6 over 7 minus 6.5. I Norton is negative 3.843 amperes. There. All right. So we got this answer. So R Thevenin, V Thevenin over I Norton is negative 4.43 559 divided by negative 3.843. 1.186 ohms, which matches that. And just to check our work, let's look at the dead network. So our dead network is going to look like short circuit 7, 3. Oh, no, the 3 ohm resistor will not be there because that's what we're trying to find the equivalent resistance with respect to. So here's our 5 ohm, this is our 2 ohm. So these are just these 3 resistors in parallel. So RTH is 1 over 7 plus 1 over 5 plus 1 over 2 to the minus 1. .186 ohms. So there we go. Once you're comfortable with doing this, you won't need to check your work all the time. And you can actually, it's usually pretty easy, especially in these circuits that only contain independent voltage and current sources. Probably the easiest thing to determine directly is the Thevenin resistance, because it's just the same resistor combination techniques that you've been doing for a couple of weeks at this point. So it may be beneficial to you guys to do that first, and then figure out what will be easier to solve for, Thevenin voltage or Norton current, and then use the resistance and whatever quantity you solve for to determine the third property. Any other questions about Thevenin and Norton equivalent circuits or anything like that, or any homework questions or anything?
I actually had a question about an earlier part that you don't have to like necessarily redraw, but we were like assuming that VA is also equal to VTH in that first circuit when you
Yes.
redo it. Can you explain that?
Absolutely. I will redraw it real quickly because it'll help show what's going on there. So we had our 18.6 volt source, our 7 ohm resistor. Here is VTH. So we've taken our resistor out. Here's our 6.5 amp source. Here's our 5 ohm resistor. Here is our 2 ohm resistor. And I said that my reference node was down here. And this guy, this node had a nodal voltage of VA. So what is the nodal voltage associated with the positive polarity terminal of VTH?
Oh, that's why, because it's VA right there.
Right, and then the nodal voltage associated with the negative polarity terminal is ground. So VTH is VA minus 0, or VTH is VA.
Okay, thank you very much.
No problem. Any other questions or anything here? All right, so one last thing that it may not be super obvious from what we've done today is that once we know the Thevenin voltage and the Thevenin resistance and the Norton current, we can draw a Thevenin or Norton equivalent circuit. So in this case, that would be, let's see, plus minus negative 4.559 volts, 1.186 ohms. And here is our 3 ohm resistor that we were finding everything with respect to. And similarly, we can have negative 3.843 amps. (1.186 ohms). And there's our 3 ohm resistor. So we made everything that isn't the 3 ohm resistor look like either this Thevenin equivalent circuit or this Norton equivalent circuit. So on your exam, when I ask you to work problems using the maximum power transfer theorem, using the Thevenin and Norton equivalent is a possibility for you guys to use, in addition to potentially just using multiple iterations of source transformation. So I just wanted to make that that clear. They are two different ways of breaking down a circuit into a practical voltage source and a practical current source. The only real difference there is that the Thevenin and Norton equivalent circuits, or the Thevenin and Norton method, will always work. And source transformations are limited in as much as you have to have a practical source to transform and able to do anything with it. So I just wanted to put that bee in your bonnet for consideration when you're working practice problems and all that kind of stuff for your test. That's going to be next 1 week from today, right?
Yes, sir.
Yep. So the upcoming test does not officially include Thevenin and Norton equivalent circuits, but they can still be used to make your life potentially a little bit easier. So I just wanted to, have you guys thinking about that. All right, unless anybody else has something to talk about, we're done for the day, and I will catch you guys on Monday afternoon.
Thank you.
Yep. See you later.